Hello everyone, Mr. Fawcett here, and we are back for another AP Calculus lesson. Today we're going to focus on the quotient rule. So in our last couple videos we talked about the product rule, that is how do we take the derivative of a product of two functions, and I'm sure you can guess if we're talking about the quotient rule, it's going to be how we take the derivative of a quotient of two functions. Before we get there though, let's do a little warm-up problem. So you're going to rewrite this function in polynomial form and then take the derivative. So pause the video, give this a shot, and then come on back. Okay, so I rewrote the f of x function. We get 5 halves x squared plus 3 halves x minus 2. Again, just remember your exponent rules. When you're dividing terms that have the same variable, you just subtract the exponents. That means f prime using the power rule is going to be 5x plus 3 halves. So while it looked like a complicated function to take the derivative of, once we simplified and divided each term in the numerator by the 2x squared, it was pretty easy to take the derivative of, just using the power rule. That being said, I'm sure you could think of, well, there must be another way to take this derivative because today is all about the quotient rule. So would it be any easier? Would it be any harder to use the quotient rule to take the derivative of this function? Well, we need to know what the quotient rule is before we make that decision. So we're going to come down here to the quotient rule. And if I am taking the derivative of a quotient, I'm going to take the top function, so f prime of x, times the bottom. Now I'm going to subtract the top function. I'm going to subtract the top function times the derivative of the denominator, or the derivative of the bottom function. And that's all going to be over the square of the bottom function, or the square of the denominator. So this is the quotient rule. The numerator in the quotient rule is similar to the power rule, but notice that you are taking the difference of those products, not adding those together. There is a proof to this. Again, we're going to possibly save the proof for a future video. It's not necessary that you know the proof for an AP Calculus exam, so it's something good to know, but it's more important that you know how to implement this rule. So we're going to focus on that for now. So let's get rid of this, and let's look down at the problem from up above. Now, instead of simplifying the function and then using the power rule, we're going to jump right into the quotient rule. So I'm going to walk us through this one. F prime of x is going to be equal to the derivative of the numerator, or the derivative of the top function. So that is going to be 20x cubed plus 9x squared minus 8x. We multiply that by the bottom function, times 2x squared, minus the top function, and then we're subtracting the product of the top function and the derivative of the bottom. So that's going to be equal to 4x. That looks like a lot. And then we are just squaring our bottom function. So 2x squared, that product squared. We have some simplifying to do. No question about that. So I'm just going to do my distributing for both. 40x to the fifth plus 18x to the fourth minus 16x cubed. I'm going to be so I have this negative here, right? So you can either distribute this negative right away, or you can distribute it at the end. I'm going to distribute it at the end. So 4x times 5x to the fourth is 20x to the fifth, but then I have to distribute the negative. So I get minus 20x to the fifth, then I get minus 12x to the fourth, and then I get plus 16x cubed. That is all going to be over 4x to the fourth. All right, next line. Let's see what we get. I'm going to combine my like terms. So it looks like I have two terms with an x to the power of 5. So that's going to give me 20x to the power of 5, or 20x to the 5th power. I have two terms with x to the power of 4, or x to the 4th power. So that's going to give me plus 6x to the 4th. We'll use different color now. I have two terms that are x cubed. Fortunately, those simplify, so I'm left with plus 0. So I don't even need to do anything with that. And that is all over 4x to the 4th. Now I can keep simplifying this. I can factor out a 2 x to the 4th from my numerator. So that leaves me with 10x plus 3. And if I factor out a 2x to the 4th from my denominator, that leaves me with 2. So that gives me 10x plus 3 all over 2. Now you may say, well, this doesn't look like what I got up above. Well, that's just because we divided each term by 2. So if I do that, I get 5x plus 3/2. And that is what we got our first go around using the power rule. So clearly, the quotient rule was not very helpful in finding this derivative. Just like the product rule, though, there will be times when the quotient rule is necessary. And it's up to you to decide when to use which rule, right? So on an exam, you don't want to spend a bunch of time using the quotient rule. If you could, you don't want to spend 5 minutes using the quotient rule if the power rule could get you there in 90 seconds, right? So it's all about being able to use whatever tool is in your box most efficiently. So some tools may both do the job, but one just does a job quicker than the other one. So let's look at two problems. Again, you'll notice this lesson is the same structure as the product rule. So in this part, we are going to look at both of these functions and decide which one we have to use the quotient rule for, which one where no other rule is an option, or which one or where we're not allowed to use the power rule. Because technically, if we use the quotient rule, we could also use the product rule, because the quotient is just, we'd be multiplying by the reciprocal of the denominator. But for now, we're just going to think, can I use power, or do I need to use quotient? All right, pause video and write down your thoughts. All right, so for number one, we are able to rewrite this as a polynomial, which means we could then use the power rule. For number two, we can't, right? We can't simplify natural log of x over 4x squared. There's nothing to factor out from each of those terms and then simplify. So we do have to use the quotient rule for number two. We could use the quotient rule for number one. It's just going to be a little bit more messy than the power rule. Okay, let's get rid of this and let's actually get into some practice. Actually, we got to fill in these blanks, then we'll get into some practice. Okay, so if we can rewrite the function in polynomial form, or in something that's not quite a polynomial, but where we can easily apply the power rule. So a polynomial is not going to have fractional exponents, but we can apply the power rule to something like this. Right? Even though it has fractional and negative exponents, which aren't technically polynomials, the power rule still works just as good. So if we can rewrite it and it can look something like that, then a lot of times it may be easier to use the power rule than the quotient rule. But if we can't rewrite it, if we're stuck with like what we have here, then we will need to use the quotient rule. And we're actually going to go ahead and do that, perform it on g of x to find the derivative g prime. Let's clear this, actually clear everything and then move this up a bit. All right. So again, pause the video, see if you can apply the quotient rule here, and then come back and check your work. Okay, so g prime of x is equal to the derivative of the top, which is 1 over x, or derivative of the numerator. I just say top and bottom because when we're going quick, it's easier than saying numerator and denominator. But of course, if you want to be formal, you would want to say numerator and denominator. Derivative of the top times the bottom function minus the top function times the derivative of the bottom. So times 8x. I actually have an extra set of parentheses there I don't really need, but that's okay. All over the square of the bottom function. So 4x squared, that product squared. And of course, with the quotient rule, you usually have some simplifying to do. So g prime of x is equal to, if I simplify this right here, I am going to just get 4x minus 8x times the natural log of x all over 16x to the fourth. Now, the common factor between the numerator and the denominator is 4x. So I'm going to factor that out. And I'm left with 1 minus 2 natural log of x all over 4x times 4x cubed. That is going to give me, after these simplify, 1 minus 2 times the natural log of x all over 4x cubed. That is going to be my derivative g prime of x. All right, let's get into some more practice problems. We're going to start off with number 2. We're actually going to do number 2 through 5. Now, we're using the quotient rule here so that you understand the derivatives of the other trig functions that we work with. So we already know what sine and cosine were. We figured those out real early, or we were told what those were real early, because those appear more often. However, we still need to know the derivatives of these, we could say, non-familiar trig functions, because they're not as familiar to us as sine and cosine are, but they are important to know the derivatives of in case they ever appear in problems. So my hint is you may want to rewrite these in terms of sine and cosine and then apply a quotient rule or product rule or power rule, whatever you feel like is necessary. So I'd go through and do all 4 of them, then come back and see if you've done them correctly. All right, so I just put up the work for both of these because they would take quite a long time to write out on video. And you can always pause the video and look at each step. But again, the first thing I did was I rewrote tangent and cotangent in terms of sine and cosine, because I know what the derivatives of sine and cosine are, and I can apply the quotient rule. Now, there are two spots, one in each problem, that I want to talk about real quick, just to make sure we understand. And they occur here and here. Now, you'll notice that this became 1, and this became -1. And that's strictly due to the Pythagorean identity, which says sine squared plus cosine squared is equal to 1. So I think it's pretty clear over here on the left, sine squared plus cosine squared is equal to 1, or the reverse is true, cosine squared plus sine squared is equal to 1. And I'm over here on the right now, if I have negative sine squared minus cosine squared is equal to -1, well, that's just because I factored out a -1, which leaves me with negative of the sum. So I get negative, and then in parentheses, I'd have sine squared plus cosine squared. So I'd have negative, and then in parentheses, I'd have 1, which is equal to -1. The derivative of tangent is something that I would know. Whether that's you memorizing it or whether that's you using it often in practice problems. And to be honest, you're going to have more practice problems where you're taking the derivative of tangent than you are of cotangent. So tangent's going to be one you're probably just going to memorize. Cotangent may or may not be one you memorize. Now here's the thing, and this is true with 4 and 5 as well, when you see the derivatives of cosecant and secant. you're likely not going to remember what they are. There's times when I just forget what they are, but I have the capability of deriving it, right? And worst case scenario is that you need to be able to do this work to figure out what those derivatives are, right? So not everything is just memorize this derivative, memorize that derivative. If you have the tools to figure those derivatives out, it's okay if you don't have all them memorized because you can eventually get there. You can derive it on your own. If you don't have the tools to figure out what the derivative of tangent is, then if you forget what it is, or it slips your memory on a quiz or a test or something, then you're going to be out of luck, right? Because you don't know how to derive it. So learn the process. That can bail you out if your memory fails you with just a specific derivative. All right, last thing we're going to do is do 4 and 5, then we're going to call it for this video. So pause if you haven't already and attempt 4 and 5. All right, so that finishes 4 and 5. Again, go through the derivatives just to make sure you understand each step. Right here, we just split the quotient up into a product of two quotients, right? Because I could simplify these two individually and come up with a final answer. Same thing here, split it up into two quotients, the product of two quotients, and arrived at an answer. You are not going to memorize these. I mean, you might, and more power to you, but the idea is you know how to find these derivatives if you ever have to use them on a quiz or exam. Because you could run through this derivative, once we get good at the quotient rule and simplifying trig expressions, you could run through this derivative in, about 60 to 90 seconds. So it's not going to cost you too much time by not memorizing. Again, if you just try to memorize and you forget or you make a mistake with a sign or a different trig function, you're out of luck if you can't get there on your own. So let's pause here. I'll see you for part 2. As always, enjoy the rest of your day.